Okay, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1203. Hopefully you guys are doing well. It feels like forever, actually. Especially with a little mix-up I had with class last time. Last time, when I taught your class, I accidentally tapped on the other class and did the notes for your class in their class notes. And then, so now I got confused about what I taught them versus you. And it was a whole mess. And now it's like, wait, did I tell them about this? I feel like I would have told the other class about it. And it was true. I just did it in the wrong notebook. So yeah, it happened. Which is funny because now it's like, sometimes I'm wondering, like, am I the only one paying attention to these notebooks? There was one time where I pasted the link for a whole other class. I don't know if it was for this class, but I accidentally pasted a link for the notebook to another class in one of my classes. No one noticed. No one said to me, "Hey, Jhevon, this isn't a calculus class. How come you posted the notes for a calculus class?" Yeah, if I didn't look, no one would know. Like no one said anything. It's amazing. I'm the only one who cares about my notes. Okay, so today.
Maybe no one noticed because everyone takes super good notes.
Yeah, I don't. That's the optimistic approach. When I was a new teacher, I used to always go with that approach. I've been disappointed over and over. It's not even. I don't want to get into it.
We don't have to talk about it.
Yeah, we shouldn't. Because a lot of my friends are also teachers, and sometimes I would talk about my plans with them, and I'd be like, "Oh, and I'm thinking of doing this with my class. It's gonna be great." And he's like, "Nah, most people aren't gonna even try. Yeah, a lot of people are gonna do this. A lot of people are gonna do that." I'm like, "No, no way!" And then I would do it, and what he would say would happen, and then I was like, I thought I could get them excited. Yeah, it doesn't work. Okay, so last time we did marginal analysis, which was basically just applying derivatives to economics. And essentially a marginal function, I wrote it down somewhere. Where did I write it? Yeah, a marginal function is just a synonym for derivative. That's really all it is. When I say a marginal function of something, it just really means the derivative of that thing. What was important is that the derivative could approximate this difference, which is the additional change that could happen in the function when you move one more point in the future. Okay, so we did a bunch of examples like that, and I think we actually did all of the examples I planned on. I had two main examples to do, and we got through those. And then I asked you guys to read up on exponential growth and decay, and we have this. Now, for exponential growth and decay, we're not going to actually do a lot of calculus. There will be a calculus concept in there, but at the end of the day, you're not really going to need calculus for it. So it shouldn't be a bad topic. So let's actually do that.
Wait, is this new topic that we're doing today, is this going to be on the quiz Sunday or?
No, the quiz that we're having is like the last quiz you would have gotten, right? It's just moved to this week. Like I'm not going to add anything else that wouldn't have been on it last week.
So it'll be like mostly like implicit differentiation and that stuff, fun stuff.
I don't remember the topics, but
okay,
I can remind you. Whatever those topics were, it's in the quiz. It's it's in the syllabus. Whatever those topics were, it's the same ones.
Got it. Thanks.
I'm literally just moving that quiz. I'm not putting anything else on it. So basically, we're going to do exponential growth and decay first. Sometimes this looks very thick, and then sometimes it doesn't. Oh, that looks very thin. Okay, maybe a little bit. Exponential growth and decay. It's super useful because many phenomena grow, which means increase, or decay, which means decrease, exponentially. So we have to know what that means. So we should know how to model this. So, and with that, we need some definitions. What does it mean for something to grow exponentially? Before, I like to remind you guys of a different kind of growth that you guys would have seen a lot, just to kind of draw a distinction here. Suppose P of t is the amount or size of some quantity at time t. Right? So P measures the amount of some substance or some quantity or something I'm interested in at time t. We say P of t grows linearly if, maybe I should put in both, grows or decays linearly if P of t changes increases, decreases, respectively, by a fixed absolute amount per unit time. Okay, so for example, I can say, all right, I have something that I know it has size 100 right now, but it is growing by 5 units every month. So the next month it's going to be 105, the following month it's going to be 110, the following month it's going to be 115. It's growing by the same fixed absolute value of a quantity, right? So it's always growing by 5 every month, right? Whenever something changes like that, we say it changes linearly. It grows in a linear fashion, okay? We can write P of t as, well, P of t equals A plus BT, where A would be its so-called initial amount, at time t equals 0. So how much we started with, right? And B would be some fixed amount P increases or decreases by per unit T. Okay, so my example before, A would be 100, B would be 5, right? I'd say 100 plus 5T is how this thing would grow. Every time T increases by 1, the size increases by 5. Always 5, specifically 5. So that's called linear growth. It gives it rise to the equation of a straight line. That looks like mx plus b, right? So the b is the m, the t is the x, the a is what the original b was, if we look at the equation of a line. Now, let's talk about exponential growth, because it's actually different, although the wording at first might look the same, and we'll talk about that definition. We say P of t grows, decays exponentially. If it increases, decreases by a fixed relative amount. So linear means it grows by an absolute amount. This means it grows by a relative amount. A relative amount means some percentage value or proportion of its current amount. Per unit time. Okay, so that little change can make a big difference. So I can say, all right, I have 100, but it's growing exponentially. And then I would also have to tell you, once I say it's growing exponentially, I would have to tell you what is the relative amount that it's growing by. So I could say something like it's growing exponentially by 10% of its current size. And what that means is that every month I add 10% of what was going on the previous month. And this accounts for a very different growth. So after the first month, it'll grow by 10%, it'll grow by 10. But after the second month, it's going to grow by 10% of the 110, right? It's always relative to its current amount. So it'll always be 10%, but it is 10% of its current amount. And so the second month, it would actually grow by 11, right? So instead of jumping to 120, it would actually jump to 121. And at first, this might not seem like a big deal, but you'll realize that the amount it's increasing by starts increasing. And so you don't just get a straight line of steady increase, it starts to increase faster and faster. You get like an exponential curve, and that's why the name exponential growth comes from. And we know that exponentials, they can be a little tricky. They can seem to not make a difference in the beginning, but over time, they can really like go crazy. Exponential growth is really, really fast, beyond what our intuitions can keep up with. So yeah, that gives rise to an exponential curve. So we can state the above in terms of derivatives. So let's talk about that. Let's look at exponential growth first. So P of t is some exponentially growing. I mean, I'm not going to write this word out all the time, but I'll do exponentially growing quantity. Okay, let R be the percentage of its current size that it grows by This is called the relative growth rate. It is also called the growth constant. Right, so P is just some quantity that I think is growing exponentially. Let R be the percentage of P, or the proportion of P by which it grows every unit time, relatively speaking. And let's say P 0 is the initial amount. The amount we have in the beginning. And then P of prime, obviously, is the rate of change of P, rate of growth of P. Okay, I'm gonna have to mention something here. Or rate of change of P. That's how fast it's growing per unit time. But I will mention here, it is super easy to mix these two up because they use the same words in their definition. Do not mix these up. Because to even make it even more confusing, sometimes this is called the growth rate. Although most of the time I'll use rate of growth to avoid some confusion. So there's a difference between growth rate and relative growth rate, right? Or there's a difference between growth constant and growth rate. So you have to kind of know that. It's one of those things. I wasn't the guy who named these things. So there is some cause for confusion. So growth constant or relative growth rate is the R value. Whereas if someone says, oh, I'm looking for the rate of growth of P, they really mean P prime, right? It's kind of like how we've always interpreted derivatives. Right? Then we can say P prime of T is equal to R times P of T, or P prime equals RP. And we can also add the fact that P at time 0 is equal to P naught, the original amount. So this is P at time T equals 0. This is the initial amount we call P naught. And so this here is your rate of growth. This here is relative growth rate. This here, P, is measuring the current size. So the rate of growth is a proportion of the current size. It's 10% of the current size or something like that, right? So you can state that in an equation in this way. Now, these equations do have a name. This equation here is called a differential equation. It's called a differential equation because it has a derivative in the equation. And this equation here, this is called an initial condition. It tells you about the condition in the beginning. Right? Now, those phrases are important because I will specifically ask you for things like, oh, here's an exponentially growing quantity. Here's what's happening. What is the differential equation that describes this process? And what is the initial condition? Like I can just have you state these equations, so you should know what they're called. Then we can solve this differential equation. And I'll show you how later. We won't know how to solve it until like the end of the semester. I will justify it in hindsight though. I'll show you guys later. Much later, like way towards the end of the course. Guys later. To get P equals P naught e to the RT. And this is the, and of course this is, you know, like P of T. It's a function of T. This is the exponential growth formula. We can justify this in hindsight. So if I have P is equal to P naught e to the RT, then what I can do is I could differentiate with respect to time this entire equation. We've been doing things like that. And then what you would have over here is dp dt. What you would have over here is P naught times R e to the RT, because that's how we differentiate exponentials. You'll notice that this here, I can factor out an R. And look at what's left inside the parentheses. This guy is P. This guy is your R. And this guy is your P prime, right? So if this equation is true, then it's also true that P prime is equal to RP. It turns out we can actually do this in the opposite way, but that would mean us doing something that is the opposite of differentiation, which we haven't discussed yet. There is such a thing in some sense, and we'll talk about that towards the end of the semester. So yeah, that would be the equation. So this is the main. So this is the main equation for exponential growth. This is the differential equation and the initial condition that describes exponential growth. And yeah, they both go hand in hand. If one is true, if one of these sets of equations is true, the other set is also true. So a useful metric for exponentially growing quantities is the doubling time. Time it takes for the quantity to double. Okay, so let's talk about that. Let T sub D equals the doubling time. So if we have P is equal to P naught e to the RT, this would mean that if I took time equals doubling time, TD, what would happen is I would end up with double of the original amount. So I can divide both sides by P naught. I would get 2 equals E ln of 2 equals E to the RTD. I would ln both sides. So this would mean ln of 2 is equal to RT. And so I can solve for TD to get ln of 2 over R. This is the doubling time equation. I want you to appreciate that if I told you what R is, you could find the time to double, the doubling time. And vice versa, if I told you the doubling time, you could use it to find the R. And it's worth mentioning that a very similar equation to this will hold for any other kind of size factor you want. So for example, if I were to care about the tripling time, it would be ln of 3 over r. How much time would it take to quadruple? ln 4 over r. How much time would it take to be 5 times what I start with? ln 5 over r, etc. But doubling time is something that it's a very common metric. Yeah, I think that's all I want to tell you about exponential growth. Something growing exponentially means it satisfies this differential equation. Its rate of change is proportional to its current size. Exponential growth formula, that means rate of change of P is proportional to its current size. That's also a common phrase that you would see. So instead of telling you directly that something is growing exponentially, like a problem would say, oh, assume exponential growth. Another way they can phrase it is that, oh, something is growing proportional to its current time, to its current size, with growth constant 0.05. If we start off with 100 units now, how many units will we have 17 years in the future or something like that? And you should know, oh, I should be using the exponential growth equation because they use that phrase proportional to its current size, right? So, yeah. Let's talk about exponential decay. It's very similar, except here our differential equation looks different. It has a negative in front of it. So this negative means negative. So this means that P prime is less than 0. This means that it is decreasing. Okay, so you put a negative sign in front of everything. So for exponential decay, the differential equation is P prime equals minus RP. And the initial condition, well, the initial condition looks the same actually. P of 0 is equal to P naught. So I can tell you how something is in the beginning, and I can say it is an exponentially decaying quantity. A lot of things decay exponentially, like radioactive substances, medicine in the body, things of that sort. A lot of things grow exponentially as well. Populations tend to grow more exponentially, for example, because the larger a population is, the more babies they have, the faster they grow. So a lot of things like that. Okay, so that negative sign gives you a decrease, right? So this leads to P equals P naught e to the minus RT. And this is the exponential decay formula. A common metric here is a phrase that I'm sure like you guys have all heard before. It's called half-life. It's a very common way to describe something that's decaying exponentially. So every time you hear the word half-life, it means that what the person is talking about is something that's decreasing exponentially, right? We don't use that phrase in any other context. So you'll hear that phrase a lot in chemistry, for example, and biology even sometimes. So they'll tell you about, oh, this substance has a half-life of blah, right? Or carbon-12 has a half-life of like, I forgot how many years. How many years is carbon-12? It's a lot. 5,700 something. 5,400. It's like 5,000 years. It's something ridiculous, right? Like it decays very slowly. That's why, you know, carbon is so important for life. It's something that's stable. That's always there. Life can always depend on it as a source of energy. And it bonds with so many other things, carbon. Anyway, so every time we'll talk about something, some half-life, it's something that decays exponentially. And this is the time it takes to have half of what we started with. So if something is growing exponentially, you have a doubling time. Eventually, it will double in size. If something is decaying exponentially, it's decreasing. Eventually, it's going to half in size. That's the idea, right? If the process just continues, right? And we often like to know, what is the half-life of something? If I start off with 100 grams, after how long will I have 50? Then after how long will I have 25? Then after how long will I have, you know, 12.5 and so on, right? So let's get a handle on that. Let T sub H equals half-life. If our P is equal to P naught e to the minus RT, then what that means is that if I were to plug in time equals T sub H, the half-life, I would end up with half of what I started with. I can divide both sides by P naught. This gives me that 1/2 is equal to e to the minus RT. ln both sides. I would end up with ln of 1/2 is equal to minus RT. And so I would have T equals to minus ln of 1/2 over R. And this is usually written in a different way. So if you look at this guy, the minus ln of 1/2, well, you're like, well, minus ln of 1/2, well, that's like minus ln of 1 minus ln of 2 by a log rule. And ln of 1 is 0. So this becomes minus a minus ln2, which becomes ln2. Or you can think of minus ln of 1/2 as minus ln of 2 to the minus 1, which means you have minus 1 ln of 2, which again, you get positive ln of 2. Either way, you get positive ln of 2, depending on which log rule you fancy. And you ultimately will get this equation, ln2 over R.
Wait, but that's the same as the other one.
It does look the same as the other one. Yes, I was going to point that out. Half-life equation. That's why I said exponential decay is very similar. The only difference, the only way you'll know the difference is with that negative sign. So the negative sign will show up in the main equation. The negative sign will show up in your differential equation, but almost everything else is going to behave super similarly. So the time to half is going to be ln2 over R. The time to have a third will be ln3 over R. The time to have a quarter, ln4 over R, etc. It's going to look like that. But the idea is when you plug the R into your formula, you're going to hit it with a negative sign eventually, and that's going to tell you whether it's growing or decaying. So the sign is going to be very important here. Another important fact, quantities that are compounded continuously exhibit exponential growth and can be modeled by the equation P equals P naught e to the RT. PERT formula. PERT, like that shampoo, you know, shampoo and conditioner in one. They were the first people to do it. That's what I think when I see that formula. So I remember the PERT formula. You guys are too young. You won't know what I'm talking about. I don't even know if PERT's still around. I think they're still around, but like they were the first. Like, my God, like I can shampoo and condition my hair at the same time. Like it was so freaky when it happened. Like, I'm gonna save so much time. I'm gonna like wash my hair in half the time. Okay. All right. So in this section, a lot of the problems will be word problems. So because I'm too lazy to type those out, I did, you know, would it be nice to move in here? Okay, so this handout is also on the class webpage. Can be found on class webpage. Right, so here I kind of summarized all the formulas for you guys. So exponential growth is the first set. Exponential decay is the second set. You'll notice that the only thing is whenever we're putting in the formulas relating R and P is that the R takes on a negative sign in the exponential decay formula. But the other formulas are pretty much exactly the same. The only difference is, you know, when you have e to the x versus e to the minus x, you get the increasing versus decreasing curve. That spoke about continuous compounding there, but that's pretty much that you don't really have to figure it out at all because it'll always be stated. Like the problem will state, hey, we're compounding continuously. They'll always say that. So what we're going to do now is we're going to get through these problems here. Which maybe I can also do that. Yeah, whenever I have to do something like semi-productive, I have to switch to the Windows machine because it's going to be okay. So I'm just doing some screen snippets of the questions here. Okay, there we go. Move this guy over here for All right, so let's actually do this. So here is our first problem. Let P of T be the current size of a population of a colony of bacteria at time T. At 10 a.m., there are 50 bacteria. You know, I walk away, I go have lunch a little bit longer than I should have. I come back and wow, there's 350 now, right? So assume that the rate of growth of the population is proportional to its current size. So that phrase right there, that indicates exponential growth. That's what screams at you right there. So if the problem doesn't say, oh, assume it's growing exponentially, they might throw in a phrase like, oh, it's growing proportional to its current size, or it's growing by a fixed percentage of its current size, or blah, 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 right? That's them telling you it's exponential growth, right? So A, what is the relative growth rate? What is that asking us for?
R.
R. We want this. We want R. How do we find R? Well, we know that let T equal time in hours. So we can say T equals 0 corresponds to 10 a.m., right? And when do I come back? 3 p.m. So that's what, 5 hours later? So, which would mean that T equals 5 is going to go with 3 p.m. So what we're given that P of 0 equals 50 and P of 5 equals 350. That's what that sentence told us, right? So at 10 a.m., which for me would just be time 0, that's where I start the stopwatch. And at 3 p.m., they're 350, right? This was 5 hours of elapsed time. Measure time in hours, I can get these two equations, right? So of course, this guy here is our P naught, because we know what the definition is. P naught is the amount we have at time 0. This guy here is obviously going to help us find what the R is. So we do know, since P equals P naught e to the RT, this means that we have 350. We have 350 equals 50 e to the R times 5. Whereas, let me put P naught in red, so you know what I'm talking about. Right. So the P naught goes in that position, and the thing that goes with the second equation goes in those two positions. When time is 5, the amount I have is 350. So now I can start to notice that R is now my only unknown. I can solve for that. This means 350 over 50 is equal to e to the 5R. Of course, this goes into that, this goes into that 7 times. So you get 7 is equal to e to the 5R. ln of 7 equals 5R. And so R is equal to ln of 7 over 5. And that is our relative growth rate, ln of 7 over 5. Okay, and that's how you'd leave the answer, because we can't use calculators or anything. Next question. Find a formula for P of T. Well, we know what that is. We know that P of t is equal to P naught e to the RT. This means that you go and you plug those guys in. This means that you have P is equal to P naught, we know is 50, e to the ln of 5 over ln of 7 or 5t. That's it. You would stop there. You could rewrite this. It's actually equivalent to writing something like 7 raised to the t over 5 power, 50 times 7 raised to the t over 5 power or something like that. But we don't really need to worry about that. I'm fine with you leaving the answer this way. C. What is the size of the population at 4 p.m.? So we want size at 4 p.m. So this is, what would be the size at 4 p.m.?
Would you just plug in the time into t of the equation we just found?
Okay, well, what is time here?
Well, it's in hours, so it'd be 6.
Yep.
After
so
6.
This is P of 6. That's all it is. So you're just going to plug that in. And so this is going to be P of 6 equals 50 e to the ln of 7 over 5 times 6. And that's your answer. Like it's surprisingly easy. Don't get suspicious. Don't be suspicious. Don't be suspicious. Don't be suspicious. It's going to be, this problem is going to be easy. Like once you know the equations, like if you know the equations and you know what they mean, an exponential growth or decay problem is like a giveaway on an exam. It's going to be surprisingly easy. Especially compared to all the other stuff you're doing. Now it's just like, oh, I have this formula. I just need to plug in this number right here, and you're done. You don't have to do any calculus or anything. However, it is an important idea for you guys to know about. And the calculus will come in actually the derivation of the formulas. Like we have these formulas because of calculus, but once we have them, you don't really need to know the calculus to use them. D. So D asked for the rate of growth at 4 p.m. Okay, so this is, what would the rate of growth at 4 p.m. be? Like what quantity or expression do we want to calculate?
P prime.
P prime. We want P prime of 6. Now we know P prime is equal to R times P. In other words, P prime at 6 is going to be equal to R times P of 6. And so this is going to be ln of 7 over 5 times the previous answer, times 50 e to the 6 ln 7 over 5. And that's the rate of growth at 4 p.m. So you want to know how fast is the population increasing right now at 4 p.m. That's how fast, right? Of course, you can plug it in a calculator and you can get a number, but for us, you can leave it like that. When will the population have size 1500? What is that asking for?
You gotta put P as 1500 and then set that equal to the P naught.
Right.
T.
We want T such that P is equal to 1500. After how much time will the size of the population be 1500? So this becomes 1500 is equal to, so obviously we're using P is equal to 50 e to the ln of 7 over 5t. So it's equal to 50 e to the ln of 7 over 5t. And so here I'd have 1500 over 50 equals e to the ln of 7 over 5t. 50 goes into this, 5 goes into 15 3 times, so you get 30 here. So then you get ln of 30 equals ln of 7 over 5t. And so you get t is equal to 5 ln 30 over ln 7. And that's it.
I have a question.
Yes.
Is 5 ln 30, I might be wrong, I don't know, but isn't that 30 to 5 raised to the 5th, or no?
It's the same as ln of 30 raised to the 5th.
Okay, you still keep the ln. Okay, I thought so.
Yeah.
Okay.
Let's move on to problem 2. Okay, so here, the half-life of a radioactive substance is 30 years. Suppose we have a 200 milligram sample of the substance. P of t is the mass remaining after t years. Okay, so we have an exponentially decaying quantity. We know that because it uses keywords like half-life and radioactive, right? So that tells you exponential decay. Right? Just the fact that those words are used. All right, suppose I have a 200 milligram sample. A, what is the differential equation satisfied by this? What is the differential equation that we need to satisfy? Well, it would be P prime equals minus RT. So we need R to actually plug in. How would I find R here? We can go back up to the page that with these formulas that hopefully we'll have memorized. Of course, we're dealing with exponential decay, so it's the second box that's important. Can you give me an idea? What?
ln of 2 over r.
Right, you can use the half-life equation. They told us the half-life. So we know the half-life is equal to ln 2 over r. They told us the half-life is 30. So this means your r is ln 2 over 30. Well, that's not the final answer. That's not what we want. It's going to be used in the final answer. So this means P P prime equals minus ln2 over 30 times P is the differential equation. FYI, chances are on a test or a quiz, I would also ask you about the initial condition. The initial condition would be the equation stating what we had in the beginning, which was 200 milligrams. So it would literally be the equation P of 0 equals 200. So if I ask you to state the initial condition, that's what you would write down. Find a formula for P of t. So B, want to find P of t now. But we know that P is equal to P naught e to the minus RT. So this is just going to be P of t equals P naught 200 e to the minus R, which we now know is ln of ln2 over 30 t. How much will remain after 75 years? This is just, of course, we want P of 75. So that's just going to be P naught 200 e to the minus ln2 over 30 times 75. And that's that. D. After how many years will the mass be reduced to 1 milligram? That's what that's asking. So of course I would plug in 1 over here, starting with 200 over there, ln2 over 30 times t. So this means I have 1 over 200 equals minus ln2 over 30 times t. This means my t is equal to minus 30 ln of 1 over 200 divided by ln of 2. And that's that. Wait, is this negative? Is time negative here? Note. This is a positive number. It had to be. ln of 1 over 200 is actually negative itself. Also, right, because we know how ln looks, right? At 1 is where it passes through 0. It's above the horizontal to the right of that. It's below the horizontal to the left of that. 1 over 200 is a number between 0 and 1. So the ln is going to be under the curve. Also, you could realize that ln of 1 over 200 is just minus ln of 200. And so you could also think of t as 30 ln 200 over ln 2. And that looks now positive. So you won't freak out that, oh, negative time, we're going in the past, back to the future. So now, yeah, that's that. ln of 200 is positive, ln of 2 is positive. So you get a positive answer there.
Honestly, looking at that, I'm just thinking like, oh yeah, like it's decaying, so the time's negative.
Oh, yeah, no, it's still positive. Because decay means as time moves to the future, it's getting smaller. So if I have 200 now, when it hits 1, it would have decreased. I know that's happening in the future. So yeah, no, you don't have negative time. we're never gonna, you're never gonna have negative time until you get to some really crazy classes. Time should always be positive for the most part. E. It's minus 2 o'clock, sir. What is rate of growth at the time there's 1 gram remaining? Now remember, rate of growth, that's talking about P prime. So this is using P prime equals minus RP, because we're doing decay. And so this would mean P prime equals minus ln2 over 30 times, well, 1. They told us that 1 was remaining. So this means that the rate of growth is minus ln2 over 30, which is negative, and that makes sense in this context because that's a derivative. Negative means it's decreasing, and we do expect it to be decreasing at this point. Should be negative. Since we're decreasing. Okay. That's that. So we're going to move to that now. So as I mentioned, this guy, this phrase right here, compounded continuously, means exponential growth. Okay, so all the exponential growth formulas will apply to this example, right? So let's say a mythical bank is paying you 5% interest compounded continuously, and suppose you deposit $4,000 here. Let's talk about how your money is going to behave. So A, write down a differential equation together with an initial condition whose solution will give the amount in your account at any time t after your initial deposit. So this will be differential equation with initial condition. We want P prime equals RT, comma, P naught, P of 0 equals P naught. Now here, the thing with the bank accounts is the percentage, the fixed percentage is going to be the proportion. So they're pretty much telling you that the 5%, well, that's R. They're telling you the R value here. But when you plug it into the formula, you write it as a decimal. So this means that we have P prime is equal to 0.05 times P, and P naught, P of 0 equals P naught. That's the initial amount that we invested. So that's 4,000. So this part is the differential equation. And this part over here is your initial condition. And that's part A. At what rate is your account increasing when the balance is 6,000? So we know that P prime is what they're asking us for here, equals RP. And I know what R is 0.05. So this is going to be P prime is equal to 0.05 times 6,000. And whatever that is. C. How long will it take for the principal to reach 5,000? So if we started off with $4,000, how long before we have $5,000? So what we're going to do is we are using P equals P naught e to the RT because we're compounding continuously. So this means when the current size is 5,000, if I started with 4,000, growing at 5%, how long would it take for that to happen? So of course, this means that 5 over 4 is equal to e to the 0.05 t. This means that ln of 5 over 4 is equal to 0.05 t. This means that t is equal to ln of 5 over 4 divided by 0.05, which, I mean, .05, that's just 5 over 100, which is 1 over 20. So this is going to be 20 ln 5 over 4. Which is probably hard, right? It's very rare to have decimals in a fraction. So yeah, that's that. So, I mean, yeah, these problems, once you actually know those formulas, they're not that bad. I went through a little bit of exposition because, I mean, exponential growing and decaying is just something that you need to be aware of in science in general. So I wanted to just say a little bit about it, where these formulas came from. But ultimately, once you know these formulas, you know everything. And it's just a matter of you reading the word problem, understanding what words are mentioned, matching up to the formula. Oh, they mentioned half-life, which means I should be looking at the second box. And if they told me the half-life and I need to find R, I just use equation 4, right? If you just know what equation to use based on what information you currently have. And yeah. So that is exponential growth and decay. And I was going to maybe start related rates today, but obviously that's not going to happen, which is fine. It's a completely different topic. So it would be like, it's fine that we can just start that with next class. But I would encourage you to actually read that handout, maybe even try a few of the problems. Read up for next class. I think I saved. So we're going to do related rates, which is one of those big applications of derivatives. It's one of those longer type word problems. that's what we're going to do. It's going to be a 6-step process that I'm going to teach you guys how to do next time. And so I guess you can start memorizing what these guys are, start reading through them. Eventually, I want you to know what to do based on the fact that you just remember what's written in bold. But I kind of went through and explained like what each step would be here. And we'll talk about that next time. But for now, we'll end there. Yeah, and that's that. Okay, thank you for your time and attention. I have an office hours with someone in a few minutes, so I'm going to run. I will see you guys in the next one. Ciao.